In this lesson, we're going to work through some application problems using exponential equations. And we can start off by recalling the formulas for compound and continuous interest. If you remember, the balance in a bank account as a function of time is equal to the principal amount times 1 plus the rate divided by how often it's compounded. All of that raised to an exponent of the number of times it's compounded by the number of years. That is for compound interest. And then we also have one for continuous interest. The balance in a bank account is going to be the principal amount, and this time it's times e to the RT, where the rate is explicit. That's the continuous rate. So whenever you see the word continuous, you know you got to have a base of e, continuous. All right, so now we can solve for the time or the rate. So we'll start here. A sum of $5,000 is invested at an interest rate of 9% per year. So that's the nominal rate that the bank will give you, which I have no idea what this must be like a stock market thing, because you'll never get 9%. Find the time required for the money to double if the interest is compounded semi-annually and continuously. Well, what we did in the previous unit was we had to use our graphing calculator to solve that, but now we don't need to do that. We can actually solve this using our exponential equations. So for part A, we're going to list the reasons here. Part A is, or list what we know. We want semi-annually, that means twice a year. So n is going to be 2, and the rate, the nominal rate is 0.09, and then the principal amount is 5,000. And if I want my money to double, that means the balance at a certain time, if I double the 5, it's going to be 10,000. So we're going to start with those values. So now we're going to enter these into our formula for compound interest. My final balance is 10,000, and my initial is 5,000. And then I'm going to use the formula 1 plus 0.09 divided by 2, and I'm going to raise that to the 2t. So when I simplify all this, the 5,000 divided into the 10,000, that's just going to be 2, which directly ties into the fact that you're doubling something. We'll talk about that in a little bit. And it is times 1.045 to the 2t. It's an exponential equation. I'm going to solve by taking the log of both sides. So I have the log of 2. I'll take the common log this time. And by taking the log on this side, I'm going to bring the exponent down. 2t times the log of 1.045. Okay? And then I got to solve for t. So I want t by himself, which means I got to divide away the 2 and the log of 1.045. So let me show you that. If I divide all this stuff away, I'm left with a solution for time. So this is probably slightly easier than graphing it and choosing an appropriate window. This is the algebraic way of solving. So my final value for time, my exact value, is log of 2 over 2 log of 1.045. And actually, let me put the 2 in parentheses too, because I don't want you thinking you can reduce those 2's down. You can't. If you evaluate this, you get t is approximately 7.9 years, almost 8 years, to double your money. So now we're going to figure this out if we are compounding continuously. I have my same principle, 5,000. When I double it, I get 10. And then for continuous functions, all I need to know is that the rate is 0.09 again for the 9%. So as I enter things in, the 10,000 over here, the 5,000 on the other side, what you're going to see is that once you divide the 5 into the 10, you get 2 again, and that represents the doubling time. That's e to the 0.09t. This time, to solve it, I'm going to take the natural log of both sides because that's going to get rid of the natural log of e. So the natural log of 2 is equal to, if I bring the exponent down, I get times the natural log of e, but the natural log of e is 1, so he goes away. And I have the natural log of 2 is equal to 0.09t. I get a much simpler expression. It's the natural log of 2 over 0.09. So it's the natural log of the fact that it's being doubled divided by the rate. And in this case, t is approximately 7.7 years. So it takes slightly less time to double your money when you are compounding continuously than when you're compounding at a set rate. So we can also solve for the rate in different examples. Here's our example. A sum of $2,000 was invested in an account where the interest was compounded continuously. So you see that word, what formula are you going to use? After 1 year, the amount was $20.94.15, and I want to figure out the interest rate. So let's write down what we know. The principal amount, I start with 2,000. Time is just 1 year, so t is equal to 1. And the balance in the account, we'll say b of t, or b of 1 actually, since I know that, is $2,094.15. Since it's continuous, you are using the continuous function, so the balance is equal to the principal times e to the rt. And then we just substitute in 2094.5 is equal to the original amount times e. This time I don't know the rate, but my time is 1 year. Let me see if I can erase that, if it'll let me. Okay. So I divide the two, and when I divide each side by 2,000, so I get rid of the coefficient by dividing, that turns into a number that doesn't terminate, but 0.1047075. You can leave it as a fraction, or you can write all the decimals out. That's e to the r. Since it's a base of e, I want to take the natural log, and that turns into r times the natural log of e. I always do that. I make an h instead of an ln. I don't know why. For years I've done that. Okay. We know that the natural log of e is equal to 1, so here's my rate. It's the natural log of those two numbers divided by each other. So when I put that in my calculator, I get an approximate rate. It comes out 0.046, so that's approximately 4.6%. This time I just solve for the rate instead of the time. But now that I have the rate, I can figure out how long is it going to take for that account to reach 3,000. So 3,000 is on this side, 2,000 is on the other side, e to the 0.046, and this time I'm solving for time. I'm going to let you finish that, and we'll check it in class. So we model population growth quite often with an exponential function. We can model it using an annual growth rate, and that's using a growth factor. So annual growth is going to be our standard, well, we'll use P now. The population as a function of time is going to be the population at time 0, so that's P sub 0 times the growth rate times T. And again, P sub 0 is initial. That's the initial population. B is the growth factor, which is 1 plus the rate. T is time. We can also model it using continuous growth. And continuous growth is going to be with a base of e, P sub 0, that's the initial again. This time we have e to the rt. And again, r is the continuous rate. Continuous rate. So you have to look at the problem and see if it's continuous or not. If you don't see the word continuous, then you're going to use this model over here. If you do see continuous, then it's this guy. So let's look at the next problem. The initial bacterium count in a culture is 500. So I start with 500. Mr. Ott later makes a sample count and finds that the rate of growth is 40% per hour. So it's not continuous, it's per hour though. Find a function that models the number of bacteria after t hours. Well, we have our initial, and that's all we need. We need our initial, and we need our growth factor. So initial is P sub 0, that's 500, and our growth factor is 1 plus the rate, so that's going to be 1 plus 0.4, which makes our final function, P as a function of time, times in hours this time, 500 times 1.4 to the t. So if I want to figure out the estimated count after 10 hours, that's a direct substitute it in and crank out an answer. Here's my function. P is a function of time. Again, is 500 times 1.4 t. So let's look at this function first. I have a rate of 40% an hour, and that's a really, really big rate. So I should expect a pretty large number. After 10 hours at 40% per hour, there should be a whole bunch of bacteria. So P of 10 is 500 times 1.4 raised to the 10th power. And you get 14,462 ish. I'm going to round up to 63 because it's 462.7. Oh, it's not going to let me erase. Well, then I'll just write it then. 0.73. So 14,463. That's what you get roughly after 10 hours. The next example we are going to set up in class, or talk about in class, but I think you can go through and read what you have here. You have City A with 5,000 people and that growth rate, and you have City B with 250 and that growth rate. So you can write the two formulas, one for A for population growth and one for B. And then we'll go over the rest of it in class about how we solve for the populations. For this last page, I just want to define the doubling time. We've been working with it a little bit, and then we're going to work through some of this in class. So the doubling time, that's defined as the time it takes for an initial amount to double. It takes for an initial amount to double. And what you'll see when you work enough of these problems is that the initial amount really doesn't matter, because if you want the doubling time, your ratio is going to be 2. If you want the time to triple, your ratio is going to be 3. So the actual final initial divide away into the ratio that you want. But we're going to work on these problems in class together. And so that'll be it for this lesson online.